Hello, ladies and gentlemen. Welcome back. We are starting a new week. This is week 9, I believe. We have 2 lessons we're covering this week, and they're both kind of a little in depth. Today, we really start talking about some algebraic concepts, and tomorrow is all about geometry. So you're getting a little crash course in both things. Some pretty major topics in both of those arenas. I hope everyone had a great weekend celebrating Father's Day. I took a motorcycle trip over across to the east coast of Florida. That's where my parents live. And we had a nice visit, and then I rode back last night, so it was all in one day, and I'm kind of exhausted, but here we are. So let's go ahead and get started. The notes for this section are attached to this assignment or material in Google Classroom, so you can print them out and follow along as I work them right here on the screen. So the first major topic we're discussing today is adding. It's actually operations with integers, adding, subtracting, multiplying, and dividing. Now, we've talked about different types of numbers before, or the classifications of numbers in a previous lesson. We have talked about what it means to be rational versus irrational. We have talked about what an integer and a whole number and a natural number is. And today we're just extending this a little further and really getting into the nitty-gritty of what happens when you have positive and negative numbers inside expressions, and how do you work with those? How do you reconcile that? So the first little subtopic I'm going to point to right here is the adding and subtracting integers concept. And so first, let's refresh on what an integer is. So an integer is a negative number, a 0, which is only 1, it's 0, or a positive number, and these are whole numbers we're talking about, that are on a number line. And there's a little graphic here that we can use to sort of just refresh ourselves on this. Here is a number line, and you have negative whole numbers, you have 0 in the middle, and you have positive whole numbers that go this direction. Negative goes the other direction. And the rules that you want to live by when you're adding and subtracting integers is that if you have an operation that says plus minus, that means that you are subtracting that number. You're going to reduce the number by whatever the quantity is. And if you have a minus minus, that just means that you're going to add them. So we're going to do some examples so you know exactly what I'm trying to say. And let's start right here with number 1. And this says 3 minus negative 5. And sometimes you might hear me say like 3 minus minus 5. And I'm doing that because minus minus is supposed to be like a trigger for you, and you're supposed to hear it and say, oh, I need to add those. Like that means addition. So whenever you have the operation, which is minus, and then the sign on the number being negative right here, okay, there's a difference here, right? So this symbol in between the two numbers is the operation that you're going to be doing. It's the addition, subtraction, multiplying, or dividing. And then this minus sign that's in front of this number is actually a negative sign that is attached to the 5. And so like if I was looking at a number line, right, like here's a number line, I'm probably going to erase this so you don't really need to draw this. But if this is 0, right, and we go 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, we have a positive 5 this way and we have a negative 5 this way. So this number right here is this negative 5. It's at this position on the number line. It's not over here in the positive side. It's a negative number. So there is a difference between something that is an operation, which is plus, minus, and multiply and divide, and whether something is a plus sign or a negative sign associated with a number, which would mean that it's positive or negative. So try not to get them confused, okay? Like I said, I think I'm just going to erase this because it's kind of taking up space for no reason, and then get rid of that box. So if we're going to do this operation, what we're really reading this as is we're saying start at 3 and then subtract -5. Well, when you have minus minus like this, it becomes a plus. So you're going to start at 3 and you're going to add +5. So let's demonstrate that on a number line, right? Okay, so I'm starting at 3 and I need to add 5, so I'm going to go 1, 2, 3, 4, 5. So that is 4, 5, 6, 7, and 8, and my final answer is going to be 8. The biggest takeaway here is that you can see that minus minus or minus a negative really turns into an addition problem. Okay, that's the thing that you have to remember. That is the key here. Okay, so let's move on. So number 2 is just 8 plus 7. Now, you might be wondering, like if 8 and 7 don't have a symbol in front of them that say that they're positive or negative, then, you know, how can you assume? Well, it's just something that we do in math. We leave off that plus sign. This is really +8 plus +7. You see what I'm saying? But that's a mouthful, and we don't say all that. It's just assumed that a number is positive unless you are making a note that it's negative. It's kind of like a really efficient shortcut for mathematicians. So if you have +8 plus +7, +8 plus +7, you really just have 8 plus 7. And so 8 plus 7 gives us 15. And we could do a number line, but I think you get the gist with that. The number line really is only handy if you're trying to, like, you know, do some kind of like making sure you're doing the subtraction right and everything. Because your answer might end up being a negative number. Okay, and we're going to get to that in a minute. So number 3, go ahead and try that on your own. Okay, here you have +15 plus -8. So you have a plus minus situation happening here. And plus minus, I told you already what to do here, which is plus minus becomes a subtraction problem. Okay, so really you have, I'm going to pause the video here. You pause, give this problem a try, see what you come up with. Fantastic. Okay, so we're back. What we should have come up with was 15 minus 8, because a plus minus just means subtract. And so if I have a number line, and I'm starting, let's say at like 15 up here, 1, 2, 3, 4, 5, 6, 7, 8. I go back 1, 2, 3, 4, 5, 6, 7, 8. Then I have 14, 13, 12, 11, 10, 9, 8, 7. Then 7 and 8 adds up to 15. We actually just learned that in the last problem. So this makes sense. My answer is 7. Okay, it's a positive 7. It's not negative. I'm still in the positive area. Okay, what I subtracted from 15 was not enough for me to go past 0. Okay, if I go back to my number line, it wasn't enough to make me keep counting past the 0 point to where I would get a negative number for my answer. But that's what we're going to experience next. So let's do orange. I feel kind of orange today. Let's do some orangey color. So number 4 is 5 plus -12. Well, plus minus means subtract, so this will be 5 minus 12. And so what does that come out to? Well, you need a number line, so let's draw one. And I'm going to put +5 here at the end, because that's where our starting point is, +5. And then I need to go backwards. Okay, subtract means to go to the left. I got to go back 12 spaces. So 4, 3, 2, 1, 0, negative 1, 2, 3, 4, 5, 6. Is that 12? I don't know. How many did I count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. One more. 12. So this is negative 1, 2, 3, 4, 5, 6, negative 7. So if I counted back 12 spaces, I'm at negative 7. And my answer is a negative number, because another thing you can maybe recognize is that the thing that you are subtracting or taking away from 5 is a quantity that is larger than 5. 12 is bigger than 5. So if you try to take away from that, let's put this in layman's terms. Like, let's think about, like, that old, math problem that everyone always talks about. Like, Johnny has 4 apples and, Susie takes away 2 of them. How many does Johnny have left? Well, if he had 4 and she takes away 2, then she has 2 and now he has 2, because 4 minus 2 is 2. They both have 2. If Susie wanted to take away 12 apples from Johnny and he only has 5, well, she's only going to get 5 apples right now, but he might owe her 7 more apples later because he's in debt. He's in the negative now. Okay, so think about that. That's a connection you can make there. If you only have a certain amount of money in your bank account, it's a couple $100s or something, and your landlord decided to like charge your rent earlier than normal or something, which is totally lame, and I hope that never happens. But let's say they did, and your rent is like $1,000. So like they took your $500 that you had, okay, out of your bank, right? Your bank is now, you have no actual money left. And then we go into the negative because you still owe another $500, and they paid that to the landlord on your behalf, and now you owe the bank 500 more bucks. Like, you're in debt, okay? That's kind of an example of what it means to be going into the negative, okay? So let's keep going. So number 5, we have a negative 2 plus negative 8, or a plus minus 8. So plus minus means subtract. So this is really negative 2 minus 8, okay? Now we're going to have to do a number line again. Okay, let's really hammer home this number line thing. We're starting at negative 2, and we need to take away 8, which means we need to go to the left 8 spaces, okay? We're already negative, right? Like 0 is over here somewhere. We are already negative, okay? We're going to go 8 more spaces. 1, 2, 3, 4. I should be drawing lines when I do this. 1, 2, 3, 4, 5, 6, 7, 8. That's negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10, okay? If you're already negative 2 and you take away 8 more, now you're at negative 10, okay? So let's bring that back to that bank analogy. All right, you're already, in the negative by 2. Let's say this is hundreds, right? Let's say you're negative $200 already, and then you spend $800 more dollars. I don't know how or why you would do that, but people got bills to pay. So hey, negative 200, take away another $800. Now you're $1,000 in the hole. Okay, you're negative. You owe that. Your quantity of money that you owe is increasing. Okay, you're the amount of money that you're the magnitude of how far deep you're going down this number line is getting bigger and bigger and bigger, but it's more and more negative. Okay. One last question, number 6. So you guys try this. Pause the video, give number 6 a shot. It's 6 plus negative 12, or 6 plus minus 12. What does that mean? Draw it on the number line. What's your final answer? Oh, I should have written the final answer for this, which is negative 10. Sorry. Okay. Now go ahead and do number 6. All right. So you came back. You paused it. Wonderful. You're back. Now we're going to do this problem. So we're at 6. I probably should draw a little barrier here. Okay. So let's make a number line. And this is really 6 minus 12. Okay, 6 take away 12. So you're at 6. and we're going to go 12 spaces, okay? 1, 2, 3, 4, 5, 6, this is 0. And then 7, 8, 9, 10, 11, 12. How many more spaces is this down from 0? It's 6 more spaces, okay? I don't know why I just wrote that. That shouldn't be 12. My bad. It's negative 6. So if you're at 6 positive and you go 12 spaces to the left, okay, you're now in the negative at negative 6. And that's just like an interesting little pattern because 12 is double of 6. And so like it's 6 this way and 6 this way, and you know, that's just a fun little pattern to look at. So that's the gist of adding and subtracting integers. We're going to apply some similar logic now, and we're going to do this with multiplication and division. So if you need a quick little break, now's a good time to pause, take your little break, come back. Okay. All right, so let's move on to our next topic for today, which is multiplying and dividing integers. We're still on the number line in terms of like where positive and negative numbers fall. Only this time we're doing multiplying and dividing. So we've already gone over multiplication and division, and so that is still what you're doing. What happens when you have negative numbers mixed into this is that you just need to pay attention to how many positives or negatives you have, and that will determine the sign of your answer. So I'll give you an example. I need to go into like my white space up here a little bit. Find some white space on your paper too so you can do this. I'm going to use this first example right here, which is 2 times 5 is 10, right? So 2 times 5, right? We assume those are both positives. 2 times 5, the answer here is going to be a positive 10. 2 times negative 5, so I have 1 positive and 1 negative. The answer is still going to be 10, right? It's the actual quantities of these numbers are not changing. You still have 2 of something and 5 of something, and you're multiplying them. The result is going to be the same, except when you have 1 negative and 1 positive, you have the answer becoming negative. It's sort of like it taints the whole problem, makes it negative, okay? Then you can have negative 2 times positive 5, okay? Same thing, all right? 1 negative, 1 positive, your answer is negative 10. And then you could have negative 2 times negative 5, and what would it be then? Well, you have a negative times a negative, and that always gives you a positive, okay? This is all 4 scenarios of, or combinations of, you might say, of like what you might run into when you're multiplying and dividing with positive and negative numbers. You're still going to do all the arithmetic the same. We've covered that before. The only thing you have to pay attention to now is the signs, and that determines what happens with your answer. Is your answer going to be a positive or a negative number? Well, it depends on what you're doing. So, and there's tons of examples to pick from here. We're not going to do any of these because they're already done for us, which is nice. But, you know, you can see every time 2 negatives gives you a positive, 2 positives gives you a positive, 2 negatives gives you a positive, 2 negatives gives you a positive. All these answers are positive. If the signs of the integers are the same, the answer is always positive. So you have 2 pluses and 2 minuses. 2 pluses gives you a plus, and 2 minuses gives you a plus. Okay? Same thing for the negative. If the signs are different, the answer is always negative. So negative and positive gives you negative. A positive and a negative gives you a negative. Follow these examples here, and you'll see exactly what I am talking about. Okay, so we kind of like breezed through that really quick, but pretty easy to grasp, I think. The next little piece of this, before we move on to equations, right, is right here, ordering rational numbers, okay? And so suppose that you were given a list of numbers like 4 and 1.5, so that's a decimal, and 3 over 2, that's an improper fraction, right? Because the numerator shouldn't be bigger than the denominator. And then you have a mixed number like 3 and 2/3, okay? How do you put these numbers like in order from the smallest to the largest? You kind of have to think about what do these different quantities mean exactly. A strategy that I personally try to employ when I do problems like this is I change everything to just be like whole numbers and numbers that have decimal points. I get rid of all the fractions and mixed numbers and stuff because to me that is easier for me to just put them in order. But everyone's brain is a little different with stuff like this, so don't say that I'm not going to tell you my method is like the way to do it. You certainly need to try it out and play with it a little. But the best thing to do actually for this subject is I found two really good explanations of different strategies that you can use with this. So if you're on the Google Classroom and you pull up this notes like digitally on your computer, you can click right on this link and right on this link, and it will take you to YouTube. Okay, don't try and type these in by hand because it's going to be like really hard to do. Just go on there and pull them up. If you're having any trouble viewing it, just tell me and I'll email it to you or post it on Google Classroom or whatever. So 2 really good videos to watch that kind of help explain that topic really well. Go ahead and stop my video and go and check those out. I'm gonna kind of like go through those right now, okay? Take some notes here, do the example problems that they give you, and see if you can figure them out on your own. All right. The next thing is about equations, and then the last piece is about inequalities. So we're going to approach equations from a standpoint of like word problems, so you can sort of like base this in something that is like in your actual life, in real life, that you might be able to like relate it to. So an equation, so I'm going to highlight this, right? An equation, it's just where you have a set of numbers and variables that have an equal sign. Okay, that's the key there, is that it has to have an equal sign to be an equation. Okay, equals equation. All right. And what an equal sign is sort of like is kind of like, at like the playground, right? So like at the playground, you have all kinds of equipment and stuff, and they have a seesaw, right? So like a seesaw might have a little whatever kind of base on it or whatever, and then it has a little board, and then it's got like a little bar on both sides, and so like you sit right over here and your friend sits on the other side, right? And then depending on who's heavier, then the seesaw is going to change. The side with the heavier person is going to go lower than the side with the thinner person, and that's because the weight on both sides is not equal. Okay, so an equation is where you're being told in the equation that the stuff that's on the left side of the equal sign is the same as the stuff on the right side, and that's a launching point. That's a part where you can start and say, okay, these have to be equal, so now what can I do to sort of like figure out what the thing is that's missing, okay? And that's a really good next little segue is about the thing that is missing, okay? I'm already in orange, let's do that. So this word right here, this word variables, we've sort of touched a little bit on variables in the past, like what they are, kind of loosely. A variable can be any number, okay? And that's kind of where it gets its name from, because the word variable means changing, like it's not always the same thing. Now, in equations, oftentimes the goal of the equation is going to be for you to solve for the variable, okay? It's for you to find the missing link or the thing that makes the equation become true. So let's put this in action and let's do it with an example. So you deposit $200 into your bank account, and now your balance is $750. What was your balance before you deposited the money? I know what you're thinking. This is like such an easy subtraction problem. If I now have 750 and I added 200 to that, I can just take away $200 and I can figure out what I had before that. But you can write an equation for this, and actually the problem says write an algebraic equation that models this situation. So my first question to you is, what is unknown? What is the thing that you do not have the answer to in this problem? What is the unknown thing that could be any number? Okay? And what I'm really asking you here is to define the variable. What is the variable in this equation? What is the thing that we are going to solve for? And when it comes to variables, if you have had any experience at all with any kind of algebra, a lot of times we just default to using the letter X, right? It's like a running joke, about algebra. Like, hey, algebra, stop asking us to find X. We don't know when she's coming back. You know what I'm saying? It's like a funny joke, like her, like algebra's ex-girlfriend. Like, it's funny. Anyway, it's very punny. But anyway, so like in algebra, we can make up any variable we want to. We don't have to use X. We can use any letter that we want to. Typically, they're lowercase letters. And a variable, like when you're making one up for a problem like this, it's a really good idea for you to pick something that represents the thing that is unknown. Okay, so you might use the letter P here because you're searching for your prior balance. Or you might use the word the letter B, because you're trying to find the before balance, or something like that. Like you think of something that makes the most sense to you. Or you can just use X. I mean, if you're cool with that, it's totally up to you, okay? I'm going to use P. I think P makes most sense because I'm looking for the prior balance. So let's define our variable. We're going to say our variable is P, and it stands for the previous balance. And it's the balance before I deposit 200. From this moment forward in math in general, in algebra, in any algebraic topic that you're working on, you are more than likely not going to go through all of this detail right here where you're, defining the variable and writing the whole thing out using words and doing all this. We're doing this right now so we can really show, what makes up this algebraic problem, okay? You're probably going to see hundreds and hundreds of problems like this, and you're just going to breeze through them because you have so much practice after you get through these problems. But for now, we're really going to slow it down and break it apart. So we're going to use the letter P to stand for the previous balance before I put in that $200 into my account. So let's make an equation that sort of like models this situation. If I take my previous balance, whatever that amount was, and I add $200 to it, right? That should equal 750. And I want you to let that sink in. Think about that. Think about how we constructed this, okay? Whatever I had before plus the $200 that I'm putting in according to this problem is going to total out to or equal 750 because they told me my balance is now 750. And the question is, how can I solve this now? How can I find out what the amount is that is P? What could P be? Well, P could be any number, but it'll only be one specific value that's going to make this become a true statement. And let me give you an example of what would not be a true statement, right? let's say I just looked at this problem and said, well, P is 1,000. Okay, P is 1,000. I'm just gonna say it's $1,000. All right. That makes this statement not true. It doesn't work that way, because if you were to write 1,000 instead of P and you add 200 to that, does that equal $750? And the answer is no, it's not equal. This is not true. So there's no way that P could be 1,000. There's really only going to be one specific value that P could be, and I'm going to show you exactly what we do in order to figure that out. There's a process here. It's not just let me take away 200 from the balance, the new balance, and I'll know what my old balance was. That's the logical way, but there's an algebraic way, and you have got to make sure that you're doing this the algebraic way, because that's how you're going to have to solve equations in the future. This is just a one-step equation. We only have to do one thing to get the variable solved. And in the future, you're going to have equations that have 2, 3, 4, 5, 6 steps. Okay, and you're going to want to make sure you're doing this process. There's a reason we have a process for it, so that it doesn't get too confusing and out of control. I'm going to switch pen colors here because there's a lot of stuff written and I don't want it to be too confusing. So let's use green. Let's write our equation. P plus 200 equals 750. And what we have to do is we need to get this P by itself on this left side of the equation. And right now, P is being increased by $200. So what we can do is we can get the P by itself by doing the opposite of this operation. Okay? We can take away 200 and P will be alone. Doesn't that make sense? Because if you have plus 200 and you take away 200, you now have 0, and that thing has canceled itself out. It's gone. Okay? But does that still equal 750? Question mark? No, it can't, okay? It cannot, because a fundamental truth about equations is that just like on that balance beam, right, or the seesaw, right? If two things are equal, if I do something that happens to one side, I also have to do the same exact thing to the other side. So instead of taking away 200 just from the left, I also have to do it from the right. That is just a mathematical truth. It's a law. If two things are equal, if I change one of them, I'm only allowed to do that if I change the other thing as well. So I take away 200 here. I also have to take away 200 over here. And I'm going to draw a line because that kind of helps me just keep things, like step by step. And now I have P equals, well, what is 750 minus 200? It's $550. That is the answer. It's solved, okay? This is considered solved because I have found what P equals. I have gotten P by itself. Another thing you might hear in if you watch any other algebra videos or something is you might hear the terminology isolated. That means I got the P right here, this variable, all by itself, okay? And it equals, whatever the new right side is after this transformation that I did to it, okay? And if you, take all of this away that we just did and think about the problem from your logical standpoint, if you have $750 now and you deposited 200, what was it before? You can just subtract this and you get 550. Well, look, that's what we did algebraically. P, which is the previous balance before I deposited the 200, was 550. Okay, that was a lot, I know. But solving equations is so important, and this process of canceling things out, doing opposite operations, getting the variable by itself, that's something you're going to have to do over and over and over again. So you need to make sure that you are taking your time with this and that you have really got it, okay? Next question. We're going to move on to the next example. Your local Best Buy has 25 iPads in stock currently. You can't see that anymore because I drew this big circle. Let's get rid of that. And let's go blue. Why not? Your Best Buy has 25 iPads in stock. They receive a shipment of 20 more iPads. But they also sell, this says 6, but you can't see it because I drew over it, sorry. They sell 6. What is the final inventory after these transactions? Write an algebraic equation that models the situation. So, what is the unknown? What's the thing here that you don't know the quantity of right now? What are they asking you to solve for? Okay. They want you to solve for the final inventory count after these transactions. Okay. Now, you need to come up with a letter that represents the inventory. You can use the letter I if you want, because I might stand for inventory, or you might use the letter F, like F for like final inventory. Whatever you want to call it. All right, I'm going to call it I, okay? Nice little cursive I right here, okay? I is the final inventory of what? It's the final inventory of iPads, and it's the final inventory of iPads when? It's after these transactions, okay? You might not always have to write all of this detail out, but it's good to do now because you need to really understand what is the variable representative of. What am I making a variable for, okay? And how are we going to solve for that? Well, this one actually is a little easier because the final inventory is just going to be all these transactions, like, added and subtracted or whatever, equals the final inventory count. So let's put our equal sign here, right? And all of that is going to equal I, okay? So what transactions transpired here? What happened with this inventory? Well, we started with 25. That takes care of this. They receive a shipment of 20 more, which means we added 20 more iPads to our inventory. That takes care of this. And then they sold 6 of them. So they took away 6 from their inventory. They no longer have 6 of them because they sold them to customers. So 25 plus 20 minus 6 gives me I, which is the final inventory. This one is a little easier because you don't have to do any opposite operations or anything. You just need to figure out what all this comes out to. 25 and 20 gives me 45. So 45 minus 6 equals I. And then you just need to do 45 minus 6, which is 39, equals I. And that's your answer. The inventory, the final inventory is 39 iPads here at this Best Buy. Okay, so let's move on. We're still doing equations, but we're going to be talking about multiplication and division. Still the same idea, still the same principles and concepts, but now you have multiplication and division added to this. Okay, so let's jump into some multiplication and division equations. Your hourly wage at your job is $17.50. So that means every hour you work, you earn $17.50. What algebraic expression could you use to model your total pay for any number of hours worked? Then, so this is like a 2-part problem. We got 2 things we got to look at here. Then convert this into an equation in which you earned a total of $437.50. How many hours did you work? Okay, so let's talk about the expression part first. Like, we can draw a little squiggly line here, and we'll do this on the first side, right? We'll do the expression over here. Expression. Okay, this is not showing up on my... Okay, there we go. Okay, so here's my expression side, all right? So we make $17.50 an hour. So let's use the letter H to represent the hours worked. And that's our variable. We've defined our variable because that's the only thing that really is not given to us here, right? We don't know how many hours we're working. It might change by the week. You might have a full-time job that's the same every week. Who knows, okay? But H is going to represent the hours worked. And then our expression is going to be $17.50 times H, okay? I'm going to let you in on a little trick here for algebra. many times there won't be a multiplication symbol between the number and the variable like this when they're being multiplied. So I'm going to put or. It might just be written as 1750H like this. And it is implied, I'm going to do this, I'm going to write it out for you. This is implied that it is multiplication. It's implied that it's being multiplied because it's 1750H. It's kind of like saying 5 apples. Or if A stood for apples, then 5A. Do you get what I'm saying? So that's why they do that. It's like a shortcut. Okay, so if that's our expression, now we need to convert this into an equation. We'll do this in green. Convert to... Whoa, what's that? Hold on. I picked the wrong tool. 1 second. We're going to change to green. Good. Okay. We're going to convert this to an equation in which you earned a total of 437.50. So our expression that represented our hours worked and our money, okay, 1750H, is now equal to 437.50. Think about this. This is saying you earned this much per hour. All right, so you worked some number of hours and you got this much total. Okay, so the only thing you have to figure out now is how many hours did you work? How many hours did it take you at a rate of $17.50 an hour to get to this point? So once again, we have an equation. This is a one-step equation where we need to do the opposite operation, okay, to get this variable, this h, by itself, okay? And so since this is multiplying, the opposite operation of multiplying is division. So you're going to divide this by 1750. But what did I say, remember earlier, about that equal sign? And if you do something to one side, you also have to do it to the other. So I also need to divide this side by 1750, okay? See how I'm doing that division by 1750 on both sides, the left side of the equation and the right side of the equation, okay? So once I do that, I'm going to draw this big line here because now I'm on my next step. Let's talk about what cancels out. Well, 1750 divided by 1750 is 1. It's itself. So this goes away. And all I have left here is h. The other side is 437.50 divided by 1750, and I need a calculator to do that. I can't do that in my head. Divided by 1750, and I get 25. So the final answer is h equals 25. The hours that I worked was 25. And going back and plugging this back in and looking at it, 1750 times 25 should equal 437.50 when you do it on a calculator. Okay, we're going to do the next example. This one's a little different. I wanted to sort of give you a little bit of a challenge. So I'm not going to immediately do the problem. I want you to pause the video and work on it yourself. But let's read through it first before you pause. It says, describe a scenario that this equation could model. 15x, or 15 times x, remember this is like implied multiplication. 15 times x minus 10 equals 200. So it's two things we have to do. One, we have to, make up some kind of scenario that this could fit with. And then the other thing is, then we're going to solve for x. We're going to find out what value of x makes this a true statement, okay? And this is actually a two-step equation because there's two things we have to do to solve it. Okay, so pause the video and I want you to think about a scenario that could possibly fit into this equation. Okay, so thanks for pausing and thinking about that. You literally could have come up with, anything. I mean, you could have come up with, you went to the grocery store and bought, 15 of something that costs a certain amount of money, and then you got a $10 discount, and it came out to $200. Or this could be like a paycheck, actually, if you think about it. 15 times, that's my hourly rate, times the number of hours I worked, but then I take away 10 no matter what. Like, I always subtract $10. So think about your paycheck. Like, isn't there something out of your paycheck that you're always paying every time you get paid? Yeah, like taxes, right? I mean, they're never exactly $10, but that's could be one thing. Or it could be, like if you pay for health insurance through your employer, it might be $10, $20, $30 just for yourself. And you pay that exact fixed amount every time you get paid. So this is variable, and it varies depending on whatever the amount of x is, okay? And then this part, this minus 10, is fixed. It doesn't ever change. You're always subtracting exactly 10 from whatever this comes out to be. And then we have an equation, so whatever all this comes out to is going to equal $200, so we need to figure out what x is, okay? So you could have come up with, any scenario you wanted to. I would actually love to hear what scenarios you come up with. If you want to go on the Google Classroom and just give me a little comment, or comment on this video below and tell me what you came up with. But let's go ahead and do part 2 of this problem. How about pink? Why not? We're going to solve the equation for x. We're going to get x by itself, okay? So this translates to get x alone or isolate x. Okay, they mean the same thing. Getting it alone or isolating it, it means the same thing, okay? So let's write our equation out. 15x minus 10 equals 200. We're looking to get this sucker right here by itself. So think about it like sort of like layers. Like we need to, we can't really do anything with this right now. We can't just divide everything by 15 first, because you'd also have to divide 10 by 15. And that gets kind of messy, okay? So I'm going to show you a different way to solve this that is like a better strategy. You want to get rid of this first. Get rid of this 10, okay? Because then the thing that has, this is the algebraic expression, the thing that has the variable with it is the thing that you'll be getting by itself. And then you can get it even more by itself. So let's do this by doing the opposite operation. We're going to, instead of subtracting 10, we're going to add 10 to both sides. Plus 10, plus 10. And when we do that, right, let's draw a line because we did a step. This is going to go away because minus 10 plus 10 comes out to 0, okay? On the other side, you have to, also add that 10. So 200 plus 10 gives you 210. So your new equation is 15x equals 210. And that's step 1. That's the first step of the equation. There's one more step to this because you have to get this x completely by itself. And right now it's being multiplied by 15. So in order for you to do this correctly, you're going to have to do the opposite of multiplication, which is division. You're going to divide. You're going to divide both sides by 15. Draw a big line because this is like step 1 and step 2. And then your final thing that you have here is this 15 is going to cancel because 15 over 15 is 1. That's going to be x equals, what's 210 divided by 15? Well, I need a calculator for that. And it comes out to 14, okay? So the number that makes this true, the number that makes this a true statement is 14. 15 times 14 minus 10 equals 200. This is a true statement. It's a true statement. You can work this problem out if you want in order to figure it out. 15 times 14 is 210. 210 minus 10 equals 200. Is this getting clearer? Now does it make more sense? Like 210 take away 10 is 200? Yes, totally makes sense. 200 equals 200, and that's a true statement. Okay, so that's 2 out of the 3 sections for this lesson. The next thing is going to be about inequalities. It's really not too much different. Instead of having things being equal, now we have things that are either less than or greater than. So go ahead and pause your video, and then when you come back, we're going to go ahead and start the next topic. Okay, let's move on to our inequalities topic. So an inequality means that two things are not equal. Okay, so if they're equal, then it would be an equality. And since they are not equal, one is less than or greater than the other, that would make them an inequality. They're unequal. They're not equal to each other. So here's a little like recap kind of graphic. I found this online from this website called School 21. And it does a really good job really quickly explaining all the things that you need to remember about inequalities. So we're going to use this for our notes. There's 4 symbols for inequality. So we're over here now on the symbols, right? Let's highlight this. The symbols for inequality are listed here. You have greater than or equal to, less than, or less than or equal to. Okay, we're going to go through what all those mean. Let's do some real-life examples. You are hiking on a mountain which has a summit of 9,382 feet. So the top of that mountain is 9,382 feet. Write an inequality for the altitude that you must be at. So the altitude they defined as A, that's the variable, okay? And you have to kind of simulate this problem. You're climbing this mountain, right? And if you're climbing the mountain, that means that your altitude is variable. It's changing. As you keep climbing, your altitude gets higher and higher and higher. And until eventually you hit the summit or the top of the mountain, and you're at 9,382 feet. So at any given point in time, your altitude, or A, which is our variable, has to be less than 9,382, or when you get to the summit, it could be equal to 9,382. This would not be a good example of just less than, unless the situation was you got to the very tippity top of the mountain, 9,381 feet, and then for some reason you could never go any higher, like it was illogical for you to go to the actual summit. So that's why less than or equal to is a more appropriate choice here. Your altitude is either less than or equal to the summit or the top of the mountain, which is 9,382. Okay, a second example would be a chemistry experiment in chemistry class. You need to keep the temperature of a solution above -6 degrees Celsius. Write an inequality for the temperature, which is capital T. Okay, so what they're saying is that in order for you to do this experiment, you have to keep the temperature above -6 degrees. It can't be -6, and it can't be -7, -8, -9. It has to be higher than that. It has to be above -6. So at all times, T is greater than -6. It's not greater than or equal to. It is greater than it. It absolutely cannot be -6. It can be -5 because that's greater, right? Think about a number line, okay? Okay, the next little facet here of inequalities is what their graphs look like, and that you graph inequalities on number lines. There's 2 things that you have to think about with graphing, and that is what's your starting point? Okay, so like on this graph, this is our starting point. And then where do you color the graph in? Do you go to the right or to the left? Okay, so there's a chart I'm going to have you guys fill out at the end of the notes, but if you have a greater than or a less than symbol without the equals, the little equals line underneath it, then you're going to use an open circle to demonstrate what your starting point is. And then if it's greater than or equal to or less than or equal to, then you got to fill that circle in. It's going to be like a filled in, a closed in circle. And that's how you can tell the difference on a graph, whether it can be that value or it has to be less than or equal to, or less than or greater than that value. So first example, y. This is just a variable. We don't know what it stands for. We don't know the context. They didn't give us any information. They're just saying y, okay? It's just a variable. So the number, whatever the number is greater than 3. That's what this graph represents. So 3 is our starting point. Here we are at 3, right? And since it's greater than, we're going to go this direction with our shading. So we're going to color this in this way on the number line. And because it doesn't have a little line underneath, no line there, okay? No line. Then it is an open circle, just like that, okay? And the next one's going to be an example of a closed one. So in this situation, y is less than or equal to 2. Y can be 2. It can be 1, 0, -1, -2, -3, whatever, because all these values are true. They're less than -2, okay? Or it can actually be 2 because it could be equal to 2. And that's what the little line tells us. So we're going to fill it in. Our starting point is 2, and it's a closed circle. And then since it's less than at the 2 mark, we're going to go down this way. And that's where we're going to color in the number line to represent what we have just graphed. Okay, so how is an inequality different from an equation? Because we just talked about equations, right? Well, let me ask you a question. How many different solutions could an inequality have? How many different values could you have for the letter A in this situation? All I know about A is that it has to be greater than or equal to -3. So how many numbers is that? It's really an infinite amount of numbers, because everything that's shaded here and beyond is greater than 3. Okay, so there's an infinite number of solutions that could satisfy this, okay? Because if I plug in 0 for this, 0 is greater than -3. 1 is greater than -3. 2 is greater than -3. So that is the difference between an inequality and an equation. When you have an equation, like this example here at the bottom, there is only one value that it could possibly be that will satisfy that equation and make it true. Something plus 7 equals 9, okay? Well, there's only one thing that the something could possibly be. It has to be 2, because if it was 3, then the answer would be 10, and that it wouldn't work. So that's the difference. An inequality has an infinite number of solutions, and an equation only has one solution. All right, let us continue our discussion here about inequalities. We're going to do some examples, and then we're going to talk about how we can write inequalities from a graph. We're going to fill out this lovely table that we have at the end of these notes, and that's going to wrap it up for us. So let's look at the first example. The minimum drinking age is 21 years old. Write an inequality that represents all the possible legal drinking ages, okay? So let's make a variable first, because we need to define a variable. So I think we should use A. So we're going to define A as our variable, and this is the age. That's just it. It's age. We're not going to put anything else. It's just age, okay? And this sentence right here doesn't say that the legal drinking age is 21 and that's it, and you can only drink if you're 21, because that would be A equals 21. And that would mean that if I'm 21, I can have an alcoholic drink. But if I'm younger than that or I'm older than that, if my age is anything different than 21, that would mean that I can't consume any alcohol. And we know in our lives that that's not true. So this is bad. This is not correct. So we're going to use an inequality for this, because as long as your age is 21 or older, then you're good to go. So if your age is greater than or equal to 21, then you're good to go, because if A is 21, you're fine. If your age, or if A equals 22, you're fine. If it's 40, it's fine. If it's 50, it's fine. If it's 33, it's fine. If it's 18, it's not fine. That no longer satisfies this. If A is 18, that's not greater than or equal to 21. Okay? So that's how we develop an inequality. The next example, this bullet right here, I want you to do this one. Let's read it together and then pause the video and give it a try. The maximum number of people that can fit inside a conference room is 25. Write an inequality that represents all possible numbers of people that can be in the room. So this is a conference room. It has, if you've ever, seen like in different kinds of rooms and stuff, there's usually like a sign on the wall that says, like per order of the fire department or whatever, the maximum capacity is, this many people. So that's what's happening here. This conference room fits a maximum of 25, okay? So can it fit 24 people? And the answer is, yeah, it can. Because as long as it doesn't go over 25, then we're good to go. Can it hold 30 people? And the answer would be no, because 30 is greater than 25, and that doesn't satisfy this situation. So we need to make a variable first. So let's make a variable. Oh, wait, I said you were going to do this on your own. Sorry. Okay, so pause the video and give it a try, and then when you come back, we'll do it together. Okay, so let's go ahead and do this. So let's use P to stand for people in the conference room. I'm going to abbreviate that. Okay, so P is the people in the conference room. And so P has to be something 25. Like, you need to figure out what goes in between here, right? Is it less than, equal to, greater than, equal to, less than, greater than? What is it, okay? So as long as the number of people is less than or equal to 25, so less than or equal to, then this is going to be correct. This matches what this sentence is saying to us, okay? The next question is just a little variation, a twist, if you will, about inequalities. And this is actually something called a compound inequality. And what this is saying is that, like, if you think about it, these last two problems, this was sort of like a condition. Like, in order to meet the limitation of the room, the number of people has to be less than or equal to 25. In order for you to drink alcohol, you have to be an age of 21 or older. Okay, that's something that inequalities they're useful for, is to help explain or describe like limitations on quantities or something like that, like a rule that must be followed. And sometimes you'll have, like two different numbers that something has to fall in between, and that's called a compound inequality. All it means is compound just means that there's multiple things, happening, and they're all being compounded into one problem. So the question says the number of miles you should drive on your car before you have to go get an oil change is somewhere between 3,000 and 5,000. So that's sort of like a general truth, right? Like, we know that about our cars, depending on the manufacturer, how often you drive your car, what's your car used for, if you live in like a really like smoggy environment, if your car is really hard on oil, those are all things that go into that. But for the most part, you usually get your oil changed somewhere between 3,000 and 5,000 miles. So what's happening is, first you need to figure out what's the floor, like what's the lowest, what's the lowest you could possibly have to enter this realm, this range in which you have to have your oil changed. And so the floor of that is going to be 3,000. That's the lowest amount of miles you could be at before it might be time to get an oil change. And then in between that, right, okay, you have, we're going to call it M. I should have defined my variable first. Very bad. Sorry about that. M equals miles driven, okay? So the variable M is greater than 3,000, right? but it shouldn't go over 5,000. So the variable is in the middle, right? It has to be somewhere between 3,000 and 5,000. Now, what this really says is this is an equal to problem, because you could be exactly at 5,000 or exactly at 3,000, and I would think that would still qualify you according to what this question says. Okay, so this is like the last new part, is writing inequalities from a graph. So we're going to look at a graph. We looked at graphs before. We're going to figure out what the inequality is. Just use x for the variable. On all these questions, just use x for your variable, because there's no context here. Like, we weren't given a word problem or anything, so we don't know if this is age or miles driven on a car, or hours. We have no clue, so we're just going to use x as our variable. So in all these problems, you're going to have x and then some kind of symbol, right? And then you're going to have some kind of number. So there's three things you're going to need to have for each of these problems, okay? So x is going to be, here's our starting point is 1, right? So x and 1, that's the relationship. But is x greater than or less than? Did we go to the left, which would be less, or did we go to the right, which would be greater, okay? So we went to the right here. So it's definitely x is greater than. So all the x values are over here on this shaded side of this problem, okay? Now this is an open circle, so if you have to flip back to remind yourself, right, the open circle and closed circle thing is up here, and I'm gonna have you fill in a chart in a moment that helps kind of like really solidify all that. But this is an open circle, so we're gonna leave this symbol just like this. That means x is not going to actually ever be 1. It's just gonna be some value that is greater than 1, like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever. They're all bigger than 1. Okay, so I think that was a pretty good explanation of how to do this. I want you to do 2, 3, and 4 by yourself. Pause the video, and then we will jump back in and do them together. Okay, wonderful. So we are back. On this next problem, you should have gotten x is less than or equal to... whoa, oh my gosh, my whole thing just went away. Sorry. Okay, x is less than or equal to 1. The answer here would be 1. Here we go. And then for this one, you should have gotten x is greater than -6. And then for the last one, you should have gotten x greater than or equal to 4. Okay? All right, so the last thing I want you to do is on this last page, which appears to be not loaded. So hold on a moment while I reload my file. 1 second, please. And then my wonderful table should be there at the end. Yes, there it is. Okay, this is the last thing we're going to do in this section. We're just going to complete this table. It's going to be something that we can refer back to, and it will help us remember all the rules for inequalities. So these two symbols, this is less than and greater than. Okay, so let's write that in. And this is greater than. And what was the difference when it has the line underneath? That's right, it means that it is less than or equal to. And this one is greater than or equal to. Okay. When you are graphing it on a number line, right? So this is the graphing part that I need to write that a little more clearly, I think. Sorry. Okay, so this is the graphing part. When you graph it and you draw the circle at that starting point, is it going to be an open circle or a closed circle? Well, the first two here should be open circles. And then the next two, because they have that equal to part underneath it, are going to be closed circles. So you're going to draw them and then fill them in. Here we go. Okay, we're also going to do an example. So I'm just going to use x as my variable for all of these, but you can do any example you want to, but we're going to just use something simple like x less than 2, x greater than 4, x less than or equal to 1, x greater than or equal to 10. And then I want you to draw a number line example. This is going to be a really brief, like, doesn't have to be super artistic or anything, as long as you have the idea down about what direction you're supposed to shade in and if it's an open or a closed circle. So this is going to be 2, 3, 4, 1, 0. That would be the correct order, 0, 1, 2, 3, 4. And at 2, we're going to put an open circle. I should probably use a different color here, maybe pink. An open circle, and it's less than, so we're going to go to the left. And that's my graph. Okay, next problem is x greater than 4, so you're going to put a 4 in the middle. 5, 6, go the other way. 3, 2. And let's go ahead and graph that. This should be an open circle at 4, and then you go to the right because it is greater than. That is how you graph it. Next problem. This is going to be the same thing again for the next two things, except they're closed circles. So I want you to fill in the number lines and then graph them. Pause the video while you do that. And then as soon as you unpause the video, we're going to go over them together so you can see if you did it correctly. Okay, excellent. So this one is, the entry point here is 1, 2, 3. The other way is 0, -1. This one's at 10. So how about 11, 12? The other way might be 9, 8, something like that. And then let's use our pink to color these in. So we're going to have a closed circle at 1. And that needs to go to the left because it's less than. Done. And then our final example is going to be at 10. That's a closed circle. And we're going to go to the right because it is greater than. Okay, guys, so we are finished with this topic. The next steps for you in this lesson are going to be to go on to Delta Math. There are a couple of different types of problems that you can work on there for practice. And then finally, there's going to be an Essential Ed section that you need to go ahead and get through for this. Okay, guys, thank you so much and have a great evening, and I will talk to you soon. Thank you. Bye-bye.